Hey everyone, welcome back to another video of mine, where today we're going to be solving Leetcode problem 235 titled Lowest Common Ancestor of a Binary Search Tree. So we're given a binary search tree, or a BST, and we have to find the lowest common ancestor, or the LCA node, of two given nodes in the binary search tree. So according to the definition of LCA on Wikipedia, it says that, in quotation marks, that the lowest common ancestor is defined between two nodes P and Q as the lowest node in T that has both P and Q as descendants, where we allowed a node to be a descendant of itself. And essentially what that means is that 6 is also considered to be a descendant of itself, right? And that applies for 2, 8, 0, 4, 7, 9, 3, and 5, which are all also other nodes that actually do exist within our binary search tree input. Okay, we have to basically find the lowest common ancestor of two given nodes that are actually present within our binary search tree. So in example 1, they basically visualize this binary search tree, and the inputs of P and Q, or the two nodes in this case that were given as parameters, are going to be the values 2 and 8. And if we look at that in the binary search tree, 2 is in the left of the binary search subtree, while 8 is in the right subtree of the binary search tree input rather. And essentially, they basically only share one lowest common ancestor, and that's going to be 6, right? Which in this case is simply the root, and the lowest common ancestors of nodes 2 and 8 is 6. Now, 2 and 8 are considered to be common ancestors of each other, but since 2 is nowhere close to being a common ancestor of 8, because of course they're in completely different subtrees, and vice versa for 8 and 2 as well, the lowest common ancestor that's as low in the input that we can get in this case is going to be 6, which is actually the root itself, but that is as low of a common ancestor that we can actually find for these two nodes 8 and 2. So in example 2, we have P and Q to be equal to 2 and 4, and we would output 2 because note that 2 is actually going to be considered to be a common ancestor of itself, and of course 2 will be a direct common ancestor of 4 as well, because they are following in the same subtree of the left of the binary search tree input, and so 2 would actually be the answer that we'd output here, or the node value that we'd output. And in the explanation it says that the LCA of nodes 2 and 4 is 2, since a node can be a descendant of itself according to the LCA definition. And for example 3, we have a root to be equal to 2, 1, and P to be equal to 2, and Q to be equal to 1. And so we'd output 2, or basically the P value that is actually a direct common ancestor of both P and Q. And once again, considering that a node can be a descendant of itself according to that lowest common ancestor definition. So I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll tell you guys how I would optimally solve this problem. And the code is actually very nice and simple, and once you really understand how it works, it'll probably blow your mind. But yeah, I will give you guys a few seconds to think through this problem. Okay, so before we actually get into these code, I actually just realized that they actually turned this problem on Leetcode to be a medium problem, because actually a while back it was an easy problem last time I checked, and so that's also something that I just realized and that I wanted to share in this video. But yeah, with that out of the way, let's just go ahead and dive into the code. So the very first thing that we would want to do is basically set a current to be basically equal to the value of the root, and we can do that in Python simply setting it equal to root, which is actually the way that they give us the input of the binary search tree. And once we actually set the current to be that root, now we simply have a while loop that simply monitors every single level of the binary search tree until we actually find the valid LCA of our two nodes, and that keeps going through every single lower or deeper node until we actually get that lowest node that actually is a common ancestor of both the P and Q node values. And so we'll say while our current is actually non-null. In this case, or in this problem, this would actually run forever, because we're guaranteed that there is actually a solution up in the, or down in the constraints, that when it says that P and Q will exist in the binary search tree, so we will have a guaranteed solution to be at least the root at worst or at lowest case. And so we could replace this with a while true if you really wanted to, because either way it's going to run forever. But I'm just going to say while current is actually non-null to make this as readable as possible. And once I say while cur, I basically have to have a series of conditionals to actually check if I have found that lowest common ancestor, and I can't go any deeper, or in any deeper nodes of any deeper subtrees within my binary search tree input. So the way this conditional is going to be structured is going to say if the value of the P node is greater than the value of the current node, or basically in this case set to be the root value, and the Q, I think that's what it's called, right? Yeah, Q, okay. And Q dot value, or the value of the Q node, is greater than the node value of, again, the current or root value, whatever that current value is going to be set to in this case. If that's actually the case, this signifies that I can actually go to the right of my binary search tree, and I'm going to look for a lowest common ancestor within the right subtree of my input. And the reason why is, since this actually is going to be passed in as a binary search tree and not just a regular binary tree, we know that if the value of the nodes P and Q are actually greater than the current value, which in this case is going to be initialized to the root value, if that's actually greater than for both of these nodes, that means that both of these nodes are going to be consisting of within that right part of the binary tree. Right, or the right part of the binary search tree, as that's how a binary search tree is set up, right? And you guys can see that for yourself in examples 1 and 2, right? 6 is a node, and every single value in the right subtree of the binary search tree is going to be 8, 7, 9, which are all greater than 6, and all the nodes that are actually in the left part of the binary search tree actually have node values to be less than 6, and that's why they're in the left subtree. So if this is true, if the values of the both P and Q nodes are greater than the root value nodes, then we can actually set the current to be updated to the right of the tree. So I'll just say current dot right. Okay, and we have to basically have another conditional to check for the vice versa, or the opposite of this case. I can literally just copy and paste this conditional and simply replace the operator signs to be less than rather than greater than. And essentially what this is saying is that if the value of both the P and Q nodes, if they're actually both less than the current node value in this case, which is initialized to be the root, then we know that the lowest common ancestor is going to lie within the left part of the binary search tree, or basically in a left subtree of my binary search tree input. And so again, I can just simply reset my current to be current dot left. And now our else statement is going to basically check if one of the nodes, P or Q, is greater than the current and the other is not. That means we can't actually go deeper or go in any deeper node or subtree of our input, and that means the whatever value or node value that our current is set to in this iteration, we can't go any deeper or we can't go any lower in the binary search tree input, because that would be breaking the rules, as both of these values P and Q aren't actually strictly greater than or strictly less than, and so we can't actually go any deeper or traverse any more in our input of the binary search tree, and so we'd simply return current to whatever value that's actually set to within this iteration. And actually I should say current, I did not call this resolution. And now I can actually simply return or submit this code, and as you can see, this is actually going to be accepted, and we don't actually need anything or any return statement of any value outside of our while loop, because we are actually guaranteed to have a lowest common ancestor of both nodes, as again, P and Q are guaranteed to be existing in the binary search tree input. And again, these are also some valid, I wouldn't say too important, but valid constraints that you can actually look at. The node P cannot be equal to the node Q. And all the node dot values are unique in this binary search tree. And then we have some operation constraints on the first two lines. Okay. So again, to kind of just recap what this code is doing, we simply initialize the root to be the current and store it in a current variable. And why the current variable is non-null, again, this is intended to run forever because we're guaranteed to have a lowest common ancestor actually appear in the binary search tree input. We'll actually check if the value of the both P and Q nodes is greater than the value of the current, which in this case is going to be initialized to the root. And if that's true, we know that the lowest common ancestor is going to be in the right subtree, or to the right of our input from the current node or the root, and so we'll set cur to be the cur.right using the .right keyword in Python. And if we fall in the case that these values of P and Q are both strictly less than the cur.value node, then we know that the current or the lowest common ancestor is going to be in the left subtree or in the left part of our current node, and so we can set cur to be equal to cur.left. And if neither of these things are true, meaning one of P and Q is greater than cur.value and the other is strictly less, we can't go any deeper or traverse to any lower nodes within our input, and that's the lowest we have went at this current iteration, and so we can simply return cur to whatever value it is in this specific loop of this specific iteration or level of our while loop. And that's essentially how this works. Again, I'm not too sure why they actually changed this problem to be a medium problem. I think it was fit to be an easy problem as a good starter or base for binary search tree problems. But yeah, that's essentially how this code works. As you can see, it's pretty simple code, nothing crazy, just around like 7-8 lines of code. And yeah, it works pretty efficiently. So if you guys enjoyed that solution and learned something new, please consider liking this video and subscribing to my channel. It really means a lot. And without further ado, I will see you guys in the next video. Bye-bye.